We first note that if y equals f of x is 2 quantity x minus 4 squared minus 3, this is 2f of x minus 4 minus 3. Okay? Because, of course, f of x minus 4, I'm sorry, 2f of x minus 4 minus 3 for the function f of x equals x squared. Now, if f of x equals x squared, f of x minus 4 is x minus 4 squared. We replace x by x minus 4. We replace this x by x minus 4, and we get this. So the 2f of x minus 4 equals 2 times the quantity x minus 4 squared. And 2f of x minus 4 minus 3 equals, well, it equals this. And that should be very clear. So, what does this do? Okay, we see here that we have a set of transformations of the function. Replacing x by x minus 4 requires x to be 4 units bigger in order to get the same y values, so that shifts the graph of the y equals, well, of whatever function, 4 units in the x direction. Multiplying the graph, the function by 2 doubles every y value, and that has the effect of moving every point directly away from the x-axis twice as far. And a minus 3 on the end, whatever you get from 2f of x minus 4, you subtract 3, and that moves the graph down 3 units. Okay, so that our set of transformations. We start with the x squared function. We double the distance of every point on this graph from the y-axis, from the x-axis, so that we get, for this point, we get a point that much further from the x-axis, and we get the graph of 2x squared. Then we replace x by x minus 4, so we get this graph moved over 4 units. Every point of this graph moves over 4 units to give us a point of this graph. And this is our graph of 2 times x minus 4 squared. I can't quite write that clearly, but that's 2 times the quantity x minus 4 squared. That's this graph. And then we do the negative 3. It means we move down 3 units. Every point of this graph moves down 3 units to give us the point of this final graph. And this is a graph of y equals 2 times x minus 4 quantity squared minus 3. Now we note a couple of things. The vertex of our original x squared function stays the same when we stretch the function by factor 2, and then it moves over 4 units to the point 4, 0, so that the vertex of this graph is on the line x equals 4. Now, moving this graph straight down, when we do the last transformation, shifting downward by 3 units, the vertex remains on the line x equals 4, and that's going to be important. Okay, so let's now find the x and y intercepts of the graph of this function. X-intercept occurs when y equals 0, so we would get the solution, whatever it might be, to the equation 2 times the quantity x minus 4 squared minus 3 equals 0. Replace y by 0, so this would be equal to 0. That's what we have. The y-intercept occurs when x equals 0, and this smudge here is actually a 0. We replace x by 0, and we get this expression. And of course, what I wrote down there makes no sense at all. 2 times 0 minus 4 squared. 0 minus 4 squared is 16. Negative 4 squared is 16. Times 2 gives us 32. So that's 29. That's our y-intercept. I wrote that down obviously without thinking, and I've been doing way too much of that lately. Okay, so that's a little bit of a correction. Now, that's really easy, so I kind of overlooked it. Okay, it's really easy. X-intercept is 29. The y-coordinate of the vertex is -3, and that's what I was thinking, but that's not what I was doing. Okay, now we take this equation to solve for x. Okay, we don't have room to solve it here, so I'll bring it up here. This one is easy if you pay attention to what you're doing, and you get your result. The x-intercept, we solve this equation. Well, how do we solve this equation? We add 3 to both sides, that gets rid of our 3. We then divide both sides by 2, which gives us this equation, and now we just have x minus 4 squared equal to something. When a square of something is equal to a positive number, then the something that you're squaring has to be plus or minus the square root of that positive number. And we verify that if x minus 4 is plus 3/2, square root of 3/2, that when we square x minus 4, we are going to get 3/2. Because if x minus 4 is 3/2, if x minus 4 is the square root of 3/2, then x minus 4 squared is 3/2. Okay? Also, if x minus 4 is negative square root of 3/2, well, you square the negative square root of 3/2, you still get 3/2. So this verifies the solution, and we need to understand this. We need to understand that when a square of something is equal to a positive number, that means the something that's being squared is plus or minus the square root of that number. In any case, once we get this, we're kind of over the hump. This actually then, kind of similar to the way an absolute value equation splits things into 2 equations, we will have split this equation into 2. One equation for the positive, x minus 4 is positive square root of 3/2. One for the negative, x minus 4 is the negative square root of 3. And negative square root of 3/2, not the square root of 3 over 2 as it was written. Okay, wrote it right over here. I don't know why I didn't over there, but again, keep an eye on me. Okay, so each of these is easy to solve. We get x is 4 plus the square root of 3/2, and x is 4 minus the square root of 3/2. Now, the square root of 3/2, 3/2 is 1.5. I know that 1.2 squared is 1.44, 1.3 squared is 1.69. It's because 12 squared is 144, 13 squared is 169, and those numbers should be common knowledge to anybody who's going to think about mathematics, think about numbers. So if you don't know the squares of your numbers up to at least 20, you really should. Okay, so in any case, 1.44 is closer to 1.5 than 1.69. It's quite a bit closer. So we expect that the square root of 1.5 will be much closer to 1.2 than to 1.3. I expect it's between 1.22 and 1.23, but I haven't actually worked that out. That's just kind of intuitive. So you can test me on that. Okay, so if we add 1.2 to 4, we get 5.2. If we subtract, we get 2.8. Now, when we graph this, I actually marked the points on the x-axis where the final graph goes through that axis. And we notice that this mark appears just to the right of the x equals 5 point. Here's 1, 2, 3, 4, 5. This is a little bit more than 5. Well, this is a little bit more than 5. So this kind of confirms our graph here. Now, this sort of confirms our graph. I didn't draw the graph all that carefully, and it kind of looks like the intercept here is pretty darn close to x equals 3. And we can't really see much room between this point and the x equals 3 point. Well, actually it should have been a little bit to the left of the x equals 3 point. Should have been 2.8. Another thing that we noted is that since it's 4 plus 1/2 and 4 minus 1/2, well, what's halfway between 4 plus 1/2 and 4 minus 1/2? Well, it's 4. We start at 4 and we move 1.2 units to the right. Did I say something about a half? Anyhow, halfway between 4 plus 1.2 and 4 minus 1.2 is 4. Okay, so here's 4 on the x-axis. We move over 1.2 units, and there is one of our zeros. Here's 4. We move the same distance in the opposite direction, and we have the other 0. So the 0, the vertex of the parabola lies at an x-coordinate that's halfway between the coordinates of its zeros, which is kind of interesting and a kind of an important idea. You want to pick that idea up. Okay, so now we're going to actually solve this same equation using the quadratic formula. It's actually less tedious to solve it this way. Plugging into the quadratic formula is a little more tedious, but no harder. You don't even have to know as much mathematics, but you got to do more calculation to use the quadratic formula.